Hello everyone, let's look over chapter 15, nuclear magnetic resonance spectroscopy. The NMR spectroscopy may be most powerful method of gaining structural information about organic compounds. NMR involve an interaction between electromagnetic radiation and nucleus of an atoms. We'll focus on carbon and hydrogen nuclei for analysis of organic compound. Protons and neutrons in a nucleus behave as if they are spinning. If an atom has an odd number of protons and or odd number of neutrons, it will have net nuclear spin. Examples: proton NMR, carbon 13, 15 nitrogen. Spinning charge in the nucleus creates magnetic moment. Magnetic moment equals magnetic fields. Magnetic field exists perpendicularly to axis of the nuclear spin. You can see nuclear spin and magnetic field. If normally disordered magnetic moment of atom are exposed to external magnetic field, the magnetic moment will align with field alpha spin state or against the field, that's beta spin state. The beta spin state opposing external magnetic field, higher energy spin state. Beta spin state, higher energy spin state. Alpha spin state has lower energy spin state. When an atom with alpha spin state is exposed to radio waves with just right energy, delta E, photons are observed and spin split to beta spin state. The stronger magnetic field, the greater energy gap. External magnetic fields cause electrons to circulate, inducing opposing magnetic field. Nuclei experience less external magnetic field are said to be short, requiring less energy to spin split. Nuclei surrounded by less electron density are said to be desheared. So when alpha spins are flipped to beta spins, energy is observed and atoms are said to be in resonance. Amount of energy required for each proton to spin flip tell us about its electronic environment and structures of compound. NMR requires strong magnetic field and radio wave energy. The strength of magnetic field affect energy gap. For example, as magnetic field increases 0 to 1.41, 7.04, energy gap increases 0 to this number. This is NMR instruments. We can use deuterated solvent. So this one CdCl3. This is a standard solvent. There are 4 important parts input NMR. Number 1, number of signals. Number 2, signal location. Number 3, signal intensity. Number 4, signal shape. Let's focus on number 1, number of signals. Number of signals in proton NMR spectrum indicate number of different kinds of proton in a compound. Identical protons are chemically equivalent. Such protons fall into categories of being either homotopic or anisotropy. First, let's know definition of homotopic protons. If molecule has an axis rotation symmetry, allows one proton to be rotated onto the other without changing molecule. So those protons are homotopic protons. Homotopic protons. Another test for homotopic proton is to replace protons one at a time with another. One at a time, another. So we can see same compound. So anisotropy protons. If molecules have a plane of reflection, makes one proton the mirror image of the other. We can call this an anisotropy proton. Anisotropy proton. This replacement test is universal. It will work to identify any equivalent protons, whether they are homotopic or anisotropy. If resulting compounds are enantiomers, then the protons you replaces are anisotropic. We can call this one anisotropic protons. So 1, 2, 3, 4 carbons. Sc2, you can say alcohol. This one, 2 butanol. After replacement test, you can see deuterium on this carbon on the left side. You can see deuterium on this carbon on the right side. Those protons are diistromer of protons, diisotopic protons. If protons are neither homotopic nor anisotropic, they are not chemically equivalent. Let's consider indicate protons below into proton. So these protons cannot be interchanged by rotational symmetry or refractional symmetry. We can call this one anisotropic proton. So two protons on CH group here will not be equivalent if there is chiral center in the molecule. On the left side, you can see chiral center. So these two protons are not chemically equivalent. The two protons on CH2 group, this one, will be equivalent if there are no chiral center in the molecule. There's no chiral center in the molecule. These protons are chemically equivalent. So 3 protons on any metal group. So carbon, there are 3 protons. Carbon, there are 3 protons. Equivalent to each other. So multiple protons are equivalent if they can be interchanged through either rotation or mirror image. So this is cyclohexane chairs. Have 6 equatorial, 1, 2, 3, 4, 5, 6, and 6 axial protons. Axial equatorial protons have different electronic environment. Technically, there are 2 types of proton in here, but only one signal is observed in proton NMR. Because at room temperature, The chair interconversions occur rapidly. So NMR is not fast enough to see individual structures. So average of observed only one signals. If temperature was reduced to minus 100 degrees Celsius, link flip is low enough to observe two signals. In many animal solvents, so 1% TM tetramethylsilane is added as an internal standard. We can calculate chemical shift. Chemical shift. So observe shift from TMS in Hertz over operating frequency of the instrument in Hertz. So when you use 300 megahertz instrument for benzene, we can calculate chemical equation. So 300 mega mean 10 to the 6 hertz over, you can observe 2181 hertz. When you calculate, we can get 7.27 times 10 to the negative 6. When you use 60 megahertz instrument for benzene, use 60 mega mean 10 to the 6 hertz, and you can observe 436 hertz. So we can calculate 7.27 times 10 to the negative 6. Hertz of a signal is different in different instruments, but shift relative to TMS is constant. The unit for chemical shift are often given as ppm. ppm is part per million. Most proton signals appear between 0 to 10 ppm. This is proton NMR. On the left side, you can call that downfield. On the right side, you can call it upfield. In downfield, we see de-shielded proton. In upfield, we see de-shielded proton. The shielded proton have smaller magnetic force acting on them. So they have smaller energy gap and observe low energy ratio waves. Let's check chemical shift for alkane and alkyl halide. Alkane proton generally give signals around 1 to 2 ppm. Protons can be shifted downfield when nearby electronegative atom cause de-shielding. Electronegative atoms, examples fluorine, chlorine, bromine, iodine. Electronegative value 4.0, 3.0, 2.8, 2.5. So when you see electronegative atom, next alpha proton, we can see de-shield proton in downfield. You can see 3.3 ppm. Beta proton 1.6 ppm. Gamma proton 0.9 ppm. Also, you can see no electronegative atom. So you can find proton 1.0 ppm. When you see electronegative atom, iodide 2.2, bromine 2.7, chlorine 3.1, fluorine 4.3. And then there is one electronegative atom 3.1, two electronegative atom 5.3, three electronegative atom chlorine, we can see proton 3.3 ppm. To predict chemical shift, start with standard part per million for the type of proton. So CH3, then metal proton, we can find 0.9 ppm. CH2, methylene proton, we can see around 1.2 ppm. CH, methine proton, you can see around 1.7 ppm. So let's check effect of neighboring function groups on chemical shift. The oxygen of alcohol or ether effect on alpha proton plus 2.5. This one methylene groups CH2 we see 1.2 ppm. But when you see oxygen of alcohol next to oxygen at 2.5 ppm, so we see this methyl proton around 3.7 ppm. And also methyl groups next oxygen of an ester at plus 3. So methylene groups 1.2 ppm next to oxygen at 3.0, the total 4.2 ppm. You might see methyl group near 4.2 ppm. The effect on beta proton is about 1/5 effect on alpha proton. Also, carbonyl group, so add plus 1. So methyl group, next carbonyl group, add plus 1. So you might see methyl group, so around 2.2 ppm. When electrons in a pi system, let's skip this one. You need to memorize chemical shift for protons, different electron environment. So methyl group, red color, you can see around 0.9, methane around 1.2, methyl around 1.7, and then double bond, single bond, and CH around 2. Next, alkyne around 2.5, aromatic ring, carbon, next hydrogen 2.5. Alkyl halide 2 to 4, alcohol hydrogen 2 to 5, vinyl hydrogen between 4.5 and 6.5, aryl proton 6.5 and 8, proton in aldehyde around 10, proton in carboxylic acid around 12. Let's memorize chemical shift for proton NMR. So number 4, integration. Number 3, integration. Integration on the peak quantifies relative number of protons gives rise to signals. The relative number of protons. Computer operators set one of the peaks to a whole number. Let's set this one number 1. Let it represent number of protons. The integration represents number of protons. So you must adjust the values to whole number. So if integration of the first peak is double, 1 to 2, computer will adjust the others according to ratio. 2, 2.96, 2.1, and 3.12. The integrations are relative quantities rather than absolute count of the number of protons. 3-pentanone has 2 kinds of proton. Relative integration value of 2 signals would be 2 to 3. So there are 2 hydrogen here, 3 hydrogen. But this one, total 4 hydrogen, here 6 hydrogen. So you can get 2 to 3 ratio. The molecular formula C5H10O must be known in order to know the absolute ratio actually 4 to 6. 4 hydrogen here, 6 hydrogen, 4 to 6. Let's say multiplicity. Multiplicity is the number of peaks in a given signal. In a signal, one peak. We can call singlet. 2 peaks, doublet. 3 peak, triplet. 4 peak, quartet. 5 peak, quintet. 6-pick sextet, 7-pick septet. Multiplicity results from magnetic effect protons have on each other. Consider protons HA, HB, HA, HB. Since protons align with or against external magnetic field, there will be two different magnetic environment for HA. So against and with. You can draw signals. So you can see HA appears as a doublet. Also, you can use M plus 1 to see splitting pattern of HA. So next carbon, there's one proton. So 1 plus 1 equals 2. You need to see the doublet. Doublet. Okay, consider example where there are two protons on adjacent carbon. Splitting pattern of HA. Next carbon, there are two hydrogens. So 2 plus 1 equals 3. You need to see triplet. Yeah, triplet. There are three possibilities to both HB proton against the field, one with and one against. Both HB protons with the field. So when you draw tree diagram, you can see this one, multiplicity triplet. Consider scenarios where HA is split by 3 neighboring HB. There are 1, 2, 3 proton on next carbon. So 3 plus 1 equals 4. You can see quartet for HA. When there are n number of neighboring protons are chemically equivalent, there will be how n plus 1 peaks in the signals. So remember, three key rules for splitting. Number 1, equivalent protons cannot split on another because they resonate together. Number 2, to split each other, protons must be within 2 or 3 bond distance. For example, between HA, H, and B, you can see 1 and 2 bond distance. You can call it geminal. Between HA, HB, we see 1, 2, 3 bonds distance. You can call it bicinal. Between HA and HB, we can see 1, 2, 3, 4 distance. The splitting is generally not observed because too far apart. Number 3, Empress rule only apply to protons are all equivalent. Okay, so next, J values. Degree to a neighboring proton will couple to each neighbor is called coupling constant or J values. The J value is distance between peaks. Distance between peaks. That's J value. So protons splitting each other will have the same coupling constant. For example, coupling constant AB equals coupling constant BA, the same. Okay, so sometimes recognized splitting pattern will stand out in spectrum. For example, that's ethyl group. Splitting pattern of this proton, next 3 hydrogen. So 3 plus 1 equals 4. So you can see quartet, quartet, and on the right side, this proton, next carbon, there are 2 hydrogen. So 2 plus 1 equals 3. So you can see triplet in ethyl group. And tertiary butyl groups. tertiary butyl groups. We can see singlet proton. So in isopropyl groups gives doublet and septet. So splitting is not observed for some protons. Consider ethanol. So proton bonded to carbon split each other, but hydroxyl proton is not split. Hydroxyl group, hydroxyl proton undergo rapid exchange with trace amount of acid. So hydroxyl proton react with hydronium ion to generate oxonium ion and water. And then oxonium ion react with water to get ethanol. Such exchange blocks shielding deshielding effect of the neighboring protons, giving singlet that is open broadened. Okay, let's count number of different type of proton. So you can see symmetric here. So we can count 1, 2, 3 signals in proton NMR. And next, the middle one, you can see 4 different signals. 1, 2, 3, and 4. You can see 4 signals. On the right side, you can see only 2 signals. So to analyze proton spectrums, we follow steps. Step 1, let's calculate degree of unsaturation. Step 2, consider number of NMR signals and integration. Step 3, analyze each signals and draw fragments. Step 4, assemble the fragment. Number 5, verify process structures. So carbon-13 only accounts for about 1% carbon atoms in nature. So sensitive receive oil and concentrate NMR sample is needed. So in proton carbon NMR, carbon-13 NMR, only number of signals and the chemical shift will be considered. To elucidate carbon-13 spectrum and make it easier to determine total number of carbon-13 signals. So carbon-13 NMR are generally decoupled. So we can see only singlet. So carbon-13 NMR signals generally appears between 220 and 0 ppm. Each signal in carbon-13 NMR spectrum represent unique type of carbon. So in those structures, we can see number of carbon. The first one, we can see 1, 2, 3, 4 signals. Second one, we can see 1, 2, 3, 4, 5 different signals. Third one, we can see 1, 2, 3 because there are 2 symmetry planes. So lastly, let's memorize chemical shift for carbon-13 signals. So carbonyl carbon, you can see signals between 160 and 220. And CC double bond between 100 and 150. CC triple bond between 60 and 90. Okay, so let's memorize chemical shift for carbon-13 NMR. Thank you for watching video.